Welcome back, ladies and gentlemen. We're excited to welcome our next presentation featuring Deimos Andro from Eaton as he shares side channel attacks against ICS devices.
Good afternoon, and thank you for coming. My name is Deimos Andreu, and I am a communications engineer for Eaton. I have a rather diverse background. My education is in electrical engineering, and I spent quite a bit of time circuits, microprocessor at the chip level. I also did a lot of work in designing embedded controllers. My current interest is hardware security. So I have spent a lot of time, I spent many years in security. I have consulted with different organizations in telecommunications. And today, we're going to talk about side channels attacks. And I am speaking as myself today. I'm not representing my employer. So the opinions that you're going to hear today, they are my own. And they may not reflect the opinion of Eaton. So before I start, I would be remiss if I don't mention a number of people who came before me and worked in this field. Paul Kocher originally wrote a couple of papers back in 1999. He's the one who discovered the differential power analysis. And a lot of the work that other people did are based on his on his papers. And incidentally, he is no longer with cryptography research, but that's a different story. Colin Flynn from New AE Technology, he has developed software and hardware that they are open source. And because of him, it allows researchers, security researchers like myself, to be able to play with these devices and launch these attacks and how systems behave. In addition to Colin, I would like to thank Joe Grant from Grand Idea Studios for his original work that he did in Temple's consideration when it comes down to side channels attacks. And of course, I would like to thank SecurityWeek for allowing me to do this work that I'm doing right now, this presentation that I'm doing right now. The motivation. The motivation for this presentation is primarily are ICS devices vulnerable to side channels attacks. And side channels attacks have been around for a very long time. As I mentioned, Paul Kocher was a pioneer in the field. But even going back as a teenager, I was a radio amateur hobbyist, so I was playing with teletypes, and I noticed that every time I push a key on the teletype, my oscilloscope that I have in the lab there, the trace on the screen will jump up and down. And I started playing with it, and eventually, by adjusting the gain and the time base of the oscilloscope, I was able to tell what characters I was typing at the keyboard. Side channel attacks. Side channel attacks require physical access to the device. However, that is not always the case. In other words, you can launch side channels attacks even if you don't have physical access to the device. Basically, what they are is information disclosure. The device is leaking information about the operation that it's doing. So let's just say, for example, you have a device that is doing a cryptographic operation. By monitoring the power dissipation of the device is actually leaking a lot of information that will allow us to determine what the key is. There are several types of side channels attacks. For this presentation, I am going to focus on timing and power consumption. So when we're talking about side channels attacks, we're talking about a channel that was not part of the original design and implementation of the device. So typically, when we want to build a system, develop a system, the system is going to consist of two main phases. One of them is going to be the design phase, and the other one is going to be the implementation phase. The design phase by itself is going to be pretty abstract. We're going to get some functional requirements from marketing or from other sources, and we're going to look at the mathematics and the cryptography we want to implement and the functionality of the device. The second part is the actual design. It's like what crypto we're going to use, what hardware are we going to use, the microprocessor, the process for that microprocessor, the libraries, et cetera, et cetera, et cetera. So we have, in this example here, we have the primary channel, which it's a microprocessor communicating with a computer. This could be a SCADA system, for example. And it's exchanging data back and forth. This microprocessor is performing, let's just say, a crypto operation. And by monitoring the power, we can determine what the device is doing. Vendors are not always forthcoming with information whether or not they have a vulnerability in their parts. I was recently working on a new product, and I asked the vendor the specific question: is your microprocessor vulnerable to side channels attacks? And his answer was, if you sign an NDA, I will answer your question. An NDA is a non-disclosure agreement. In other words, for him to be truthful, I have to make a promise that I will not talk to anyone else about it. Okay, we'll start with timing analysis, and let's just say we have a system that the user is going to connect to the system, and they want to check the password. A naive implementation of that will be what you see here. So the device has the password stored in the device and is receiving the password through a serial channel. So there is a loop, and I start checking one character at a time. So if none of the characters is correct, it's going to exit the loop immediately. If the first character is correct, we'll go and test it the second time, the third character, and the fourth character. Well, clearly this implementation has a problem, because if I just monitor the amount of time that the device is taking to process this the testing of the password, I can determine how many characters of what I'm inputting are correct. Another thing to keep in mind is, unlike IT system, in OT system, in our industry, accounts never get locked. So typically in your company that you work, if you enter the password, 5 times and it's incorrect, your account is going to be locked and you won't be able to try again. In the space that I'm working in, which is the utility industry, we never lock accounts because these are critical systems. And when something bad happens, you want to be able to log into the system no matter what. So There are a couple of things that we need to determine when we're launching this type of attack. First of all, we need to figure out when the micro is actually processing the password and not when the device is responding. We also need to figure out how is this, in this example, how is the serial port handled? What's the process? And also, we need to remember that relays are protection devices. Mostly in my industry, I'm working in the utility industry, in the distribution side, and most of the devices that I see day to day are protective devices, relays, reclosure controls, RTUs, and that sort of things. So these devices, their first task is to provide protection. Communications is secondary. And thus, communication runs at a lower task. So I had a device sitting around in the lab, and I said, I wonder if this is a real attack, or if this attack can actually work on the devices that we're using to protect the critical infrastructure. So I had to do some engineering to figure out, as I mentioned before, when the device was actually processing the password. And I configured the device so the password is 1234. So I started by having the totally wrong password, XXXX. The device responded very quickly. Then I had the first character correct, so the device responded. It took more time to respond. And the more characters I have correct, the longer it took for the device to respond. And now remember, this thing can be automated, and you can run a script that will send the password continuously until there is a success. So one of the lessons here is don't compare passwords directly. Use hash the password before you send it. Also, you don't need to respond when the password is wrong. That will make it harder for the attacker to launch a timing attack. You can include random delays, but as we're going to see in a few minutes, if you do a power analysis attack, it will be very easy to get around this, because when you insert random delays, the microprocessor just sits there and counts. It doesn't really do much. Thus, the power, the change in the power is minuscule. In fact, the power is not going to change. Power analysis. Okay, so semiconductor devices, just like microprocessors, for example, if you look at their documentation, you're going to see the word CMOS in. That stands for complementary metal oxide semiconductors. And what those are, you can view them as two switches. One of them is on, and the other one is off, and vice versa. So, for example, in this example here, if the top MOSFET is on, the output is going to be at logic 1 or VCC. When the top MOSFET is off and the bottom one is on, it's going to be driven down to ground. So, microprocessors, they have layers of different materials. So if you remember from high school or freshman college physics, a capacitor consists of parallel plates, and they store charge. So the voltage of the capacitor cannot change instantly. It's going to take a finite amount of time to charge. Same thing with the layout of the printed circuit boards that you're going to be using. You have wires running around, so also, if you have two wires running in parallel, that also has some stray capacitance. So it is this fact that, that we're going to capitalize here to determine what the device is doing. So by comparing the different power profiles, the device is going to tell us what it's actually doing. Okay, so devices switch synchronously. In other words, you have a clock, and in this example, for simplicity, I'm only showing two data lines. So when at the rising edge of the clock, that's when the switching takes place. So in this example, I have data 0 and data bit 0 and 1 turning on at the same time. So the power will use a unit of 2. In the next transition of the next clock transition from 0 to high, only one of these lines changes state. So you're going to see the power had dropped. Remember, I said that CMOS devices work like switches. One of them is on, the other one is off. So in this example, in this display here, I'm showing 3 states. There is the concept of pre-charge. So what happens is when the device goes through the first portion of the clock cycle, the output goes to a state that is somewhere between 0 and 1. The reason they do that, they don't know what the next transition is going to be, and they put it somewhere in the middle, so when it will transition during the next cycle, it will not consume as much power. There are 2 ways of modeling power. One of them is called the Hamming weight, and that is we measure the number of bits that they are set, and that will give us the Hamming weight. So in this example, we have 4 bits that they are set, thus the Hamming weight is 4. There is also the Hamming distance. The Hamming distance is the number of changes between T0 and T1. So in this example, it went from 1001100 to 10101. So the Hamming distance here is 3. So it's pretty obvious at this point that the more data lines I have that they are set to logic 1, the more power I'm going to consume. And the relative power is proportional to the Hamming weight. I mean, we expected that. Because again, the more lines I have, the more data lines or address lines I have to raise from 0 to high, the more power I am going to consume. How do I measure power? There are primarily 2 ways of measuring power. One of them will be to insert a small resistor in series with our microprocessor. And by measuring the voltage across the resistor, we can determine what the amount of power that is consumed. The other method is by using a probe, a magnetic field probe. So again, the field is going to depend, is proportional to the current that is flowing through the device. So as I mentioned before, I am grateful to New AE Technology because they make they have like everything they have is open source, so you can build it yourself. So, for example, to buy a differential probe for a scope it costs thousands of dollars, while I can build my own, or you can buy it from them for relatively inexpensively. So, and you want to have a differential probe. in order to minimize common mode rejection ratio and any power spike. So the assumption here, if there is some noise, it's going to be picked up on both sides of the resistor in phase. So when you take the difference, it's going to be minimized. And what you see here, they are actual devices that I launch attacks against. So clearly, what I'm doing here, it's going to be impossible for someone to detect this attack because this attack is passive. The only thing I'm doing is just measuring the power of the device, nothing else. The device is performing its normal operation, and all I'm doing, I'm measuring the device when the device is doing its thing. So the capture hardware that I use, it was a Fluke oscilloscope. Any oscilloscope will work. And the chip whisperer light, which is a device that has the open ADC, analog to digital converter, the front end of an oscilloscope that is able to capture the waveform of the power and download it to a computer. Okay, here is another example of attacking password using a power analysis. So what I have here, I have a screen of the oscilloscope, and it's in displaying the power as somebody is entering the password. So as you can see, if one character is correct, I have like a certain power profile. If two characters are correct, the same profile is duplicated twice. If three are correct, I get three of those, et cetera, et cetera, et cetera. So this is another way to attack power using power analysis. Even when the device has added some kind of delay in the system, because when it is doing that, the power consumption doesn't change. Differential power analysis. So in differential power analysis, I'm taking a bunch of captures and I compare them and see what is happening. And by looking at the differences between these captures, I can tell what the device is doing. For example, these two traces here are part of a cryptographic operation. At the top trace, the device was doing nothing, and on the bottom trace, the device was doing some cryptography. So you can see how the power between the two has changed. So, and incidentally, what you see here are attacks on devices that we use today. That these are devices, intelligent electronic devices that they are used in the smart grid that I had laying around in my lab. So, a modern microprocessor will look something like this. So it will have a crypto module with some secret key and some onboard read-only memory and random access memory. And it will have like a DRAM and some secure flash, where perhaps that's where we're storing the programming for the device and things of that nature. So a typical setup will look like this. I have this victim target, and I have an oscilloscope which is measuring the power through a probe, and I'm taking the output of the oscilloscope, the traces of the oscilloscope, and downloading into this computer that is running the analysis software. And in this example, the computer is also sending data to the victim target. It doesn't have to be that way. I mean, obviously, this attack here is going to be easy at some point for the victim to figure out that it's been attacked because the computer is sending to it stuff that it wasn't expecting. So we're going to change it to something like this. So in this example, I have a SCADA system. This can be an RTU, a gateway, a master station that is communicating to the target via a protocol. So DNP3 is a predominant protocol in the United States for SCADA. DNP3, it also has some new additions that provide security. One of it is called secure authentication. So what happens is there are two keys. There is a session key and an update key. The update key is stored in the device, and the SCADA master will initiate session key changes by encrypting data using this update key. So again, because we're using open source protocol and open source cryptography, we know exactly what is happening, how the device is behaving. So I can just monitor the link between the SCADA system and the target, and as I'm capturing the power at the same time, I can figure out what the device is doing, and that will lead me to extracting the key from the device. So in order to launch a power analysis, it is important to know what the device is doing, what cryptographic operation is doing. And for years and years and years, the security community has been evangelizing people to use open cryptographic algorithms. They've been using this term, security by obscurity. Don't use it. You need to make public as to use basically the standard algorithms, which have been used extensively for years, and people have used them and analyzed them to death, like AES, for example. So this type of attack, it leverages the fact that the attacker is going to know what type of cryptography the device is doing. There are several methods to figure that out. I mean, by just looking at the output, you can tell what kind of cryptography is using. But the reality is most vendors, or all of the vendors, because they want to impress people, they're going to tell you that we're using AES 256 or 128, because those are the algorithms who have been around for a long time, and they are very, very reliable. So when we do differential power analysis, as I mentioned before, we let the device do its thing. It's gonna be doing either the encryption or decryption, and we're just measuring power. So in this, and remember we mentioned earlier on that the relative power is directly proportional to the Hamming weight, like how many bits are set. So in this example, the device, if the device have input 0, 0, the Hamming weight is 7. If the device has input 11, the Hamming weight is 5, and so on and so forth. I mean, this is good, but how does that help us? I mean, I have a whole bunch of inputs here that I get the same Hamming weight. That's not very useful. So because I know what the cryptographic operation is, I can also calculate the Hamming weight for each possibility of the key. So let's just say, for example, I am using AES 128. I know the key is 128 bits. So I can calculate the Hamming weight for input 0 for all of those for the 255 combinations. And that's where the open source software becomes very useful because it does that for you. You don't have to sit down and figure this out yourself. So, okay, how can we use that to attack AES? So, AES is using, we'll take AES 128. It uses 16 rounds, and each round may look something like this. So AES is it's basically is XORing a byte of the subkey with a byte of the plain text, and then it's passing it through an S-box. An S-box is a lookup table. We'll see that in a minute. And what we're doing here, we're attacking the S-box. So we don't care what the algorithm does with the output of the S-box. That's not important. And this same attack is applied to any type of crypto operation that is using the same format. In other words, you have a plain text and a part of the key, and you're XORing it, and then you're passing it to a lookup table. I have used the same technique to extract keys from Blowfish, for example, which is very commonly used in our community. As I mentioned, the AES is using a lookup table, and this is the actual lookup table from AES. So how I'm gonna determine the Hamming weight is I'm gonna take part of the plain text that I know because I capture, and I'm gonna XOR it with all possible combinations of the key, and I'm going to look up at this table and see what the output is. And let's just say for the sake of argument, the input of the S-box here is 0, 0. Then I know that the output is 63, and by knowing this number, I can tell what the Hamming weight is, because I can look at this number and I'm able to convert it into binary and tell how many data lines are on. This is great. There are some assumptions here that you need to keep in mind, and there might be some additional engineering that needs to be done, that we're assuming here that the output of the S-box is what changes the data on the data lines, and that may not always be the case. Correlation power analysis. So I have all these captures, and I can tell the difference between the captures, but how does that help me? So we're going to use some math. We're going to use some statistics. So if I have A and B, for as long as B always increases with A, the Pearson coefficient is 1. For as long as it's always decreasing, it's -1. And if they are independent, it's 0. So I can use this characteristic to attack AES. So this is an example of using the software. Again, the software does all this work for you. You don't have to know the math behind it, or you have to give to the software the captures that correspond to the actual times that the cryptographic module is doing its cryptographic operation. So in this example, I gave the software the key. That is what you see in red there. And as you can see, it calculates the coefficient, and the highest coefficient is going to be the actual key. So Here, all of the green, what is displayed here in green, is the wrong guesses. And this is just the plot for subkey 0, for the first byte of the key. You can find right away of what the first byte what the actual key was, the first byte of the key. And this process, it doesn't take hours, it takes minutes. So to apply this, when I use that, I took about 100 captures. 100 captures, it took about less than 60 seconds. So you are able to extract the key relatively quickly. So unlike software vulnerabilities, you cannot patch this, because this is how the hardware works. I mean, in order to really fix this, you need to change the hardware. So part of the motivation of giving this talk, I just want to raise awareness of what an attacker is able to do without having, without a great expenditure. I mean, the techniques that I'm showing here, it will allow each one of you to launch this attack, because again, this is open source software. The hardware is open source. They are very, very inexpensively. So some of the lessons learned is all implementations that I tested are vulnerable to power analysis, and extracting credentials is a trivial task. And because of these open source tools, it's relatively easy to attack a system. And using the statistic model, things can happen very quickly. You can get the key out of the system in a matter of minutes. It is also possible to use the same techniques without having physical access to the system. I did some work, but I didn't have enough time to complete it. A lot of devices that we have in the field today, because we want everything to be communicating, they have built-in cellular modems for communication. It is possible to capture to extract the power component from what the cell phone is transmitting. In fact, there was a presentation maybe 5 years ago from cryptography research that show how they can extract secrets from an iPhone and an Android from, I think, like 15 or 20 feet away. So these attacks are not theoretical. This stuff is real. And if someone like me with limited resources can do that, you guys can imagine what a nation state can do. And there is a number of different techniques that we can use to prevent this. Unfortunately, all of these techniques they belong to cryptography research. So to even use any of these, you have to buy the license from them. But they're available. I mean, there are ways to protect your system against power analysis attacks. Okay, the last thought I want to leave you with, in my opinion, we need to emphasize more detection than protection. So, especially we in our community live in this fantasy world that we start with a certain assumptions that we have a modulus or some key, and we're going to protect this, and it's going to work like clockwork forever. And this is not the real world. The real world is you're going to have inside attacks, people who have a legitimate reason to be in your network. So when you design your system, figure out a way of to continue operating, even your system is going to be compromised. Assume the compromise, because it's going to happen. It's a matter of time. I mean, the NSA treats all of their systems in a permanent state of compromise. So if the NSA is not able to protect their systems, you can imagine what it is that we can do. So I think it's extremely important to design our systems in such a way that once we're compromised, we're still going to be able to operate, to have do a risk assessment and figure out how can you continue to operate even after you're compromised. It's a thought. It's just something to think about. With that, are there any questions?
Hello. Tim Casto, Lanner Electronics. We make hardware devices, so very interested in your talk today. Appreciate it. I had a question about the timing analysis. You said it wasn't necessarily to be physically accessible, but how can you assess timing over the variable delays through the internet, et cetera?
There is a very interesting talk that by two folks from MIT that they were able to extract the RSA key remotely over the internet. If you Google it, you can see what they did, and that was like again extracting the RSA key of an Apache server. And here in this presentation, I talk about AES. The same techniques can be used for RSA. Again, if you Google power analysis, you're going to find that people have used techniques to attack random number generators. That they figure out that there might be some correlation between the secret key and the public key. Again, I will encourage you to look at that. It's yeah.
Phil Dunbar, Lido Cyber. I've heard that this approach has been applied to acoustic side channels. Can you comment on that? Is that myth or reality?
This was beyond the scope of my presentation, but yes, there was a presentation, I think 2 years ago at Black Hat, where they were showing how there were two people communicating over Skype, and they were able to pick up the keyboard clicks while they had this.
What I was to understand that it was an acoustic side channel from either the CPU or from vibrations from ceramic capacitors. Does that make any sense to you?
I'm not familiar with that. Okay, thank you.